you very much, Joseph, to come all your way from Canada, from Toronto. You're amazing.
Only for this?
Only for having lunch with us and for giving this amazing talk.
With sandwiches.
As you see, Joseph did a PhD in Geneva, right?
In Geneva, yeah.
In physics.
In quantum information.
And something super foundational. And then moved to the ICFO to do a postdoc in Antonio Sin's group.
Yeah.
And then started at Xanadu like a couple of years ago.
Three years
ago, really. Okay. And it's not only me, but we are also like super happy and thankful that you came to give a talk. And also super open to discuss later all the stuff that we're doing and tell you a bit more. So thank you very, very much. And how they say, the floor is yours.
Well, thank you very much, and thank you for the invite. I have to say, yeah, I mean, I work for Xanadu remotely from Barcelona, so I'm also just very grateful to see like people. That's real. Yeah. So yeah, I'll talk about basically 3 papers from the last few years today. 2 of them are published, one quite recently. The other one is going to come out next week, early, probably. And they are all to do with something I've been obsessed with really since I started quantum machine learning, which was that I just don't think it's going to scale. And so for a long time, I really wanted to solve this issue, and I'll try and convince you that at least within the framework that we've developed, we have solved it. So the talk is about how to scale quantum machine learning models to really big models, like thousands of qubits, millions of parameters, for example. And yeah, if you want to fall asleep already, like just remember one thing. There's a TLDR, which is sort of something that goes through all of these papers, and that's one way to achieve this is to make use of the properties of commuting quantum circuits, and I'll explain what they are. I guess 2 other things before I started. There's quite a wide variety of knowledge, I understand. So it's a fairly high level talk, but I'll do my best to like explain things as well as I can. If there are any questions either here or also online, feel free to like shout and just stop me. I prefer that, I think it's better. Okay, so I'll start just by giving a bit of an overview of what we do in the quantum machine learning team at Xanadu. So we're really involved in 3 areas of study, I would say. The first is understanding how to do quality benchmarking. Typically, this is just done on numerical small circuits because we don't have access to the quantum computers yet. We have one paper that came out last year, which is fairly well known, so you might have seen it. And what we did in this paper is we took a lot of popular ideas from the literature and we coded them up and we tested them like as fairly and properly as we could against pretty basic classical models. Maybe it comes as a surprise, maybe it doesn't, but we found the classical models were better than the quantum ones. So yeah, the point of this paper was a bit to try and encourage just people to do higher quality benchmarking in the papers, because otherwise it's very difficult to really take on face value what you read in the papers. Another thing which is really a big push at the moment, which is most of the QML team and also this other team, which is led by Nathan Killoran, sorry. And what we're trying to do there is understand the type of structures and the type of symmetries that are present in quantum theory, basically, and how these relate to learning from data. So a big part of this would be looking at things like invariance and equivariance, and how that relates to certain group structures in quantum theory and so forth. The other thing, which is a big push, is looking at the quantum Fourier transform, and in particular, the something called the quantum group Fourier transform. So it's a transform over some group, and understanding how that relates to data, what sort of information and features that can extract. So yeah, that's a really big push at the moment. This paper came out, I can't remember when, not so long ago, but if you want to know what we're doing, it's a good start to read that. And then there's my obsession, which is scalable designs. So building quantum machine learning algorithms that scale. And that's going to be this talk. And this is work between myself and Shanavaz, David, in Cheyu, and these are all at Xanadu. But actually, the second work I'll talk was really done quite intensively with me and Eric Armengold was a PhD student at ICFO, Barcelona, of course. Okay, so yeah, I decided I should start like the main talk with this obligatory like controversial statement, right? Which I've already sort of said, but my statement is basically that I don't think current variational quantum machine learning will scale to industrially relevant problems. There's many reasons why you might think that's the case. Maybe the one you hear the most is like, oh, there's barren plateaus, and that is potentially a problem, but I don't think that's the main problem, actually. I think the main problem is the way that we calculate gradients in circuits, in parameterized circuits. So, okay, people doing quantum machine learning, I guess will know this, but in case people don't, there is a method to calculate gradients when you have a parameterized quantum circuit, and it's called the parameter shift rule. And it's sort of the standard thing, and it's the only thing which works in general, I would say. The problem with this rule is what you need to do is for every parameter that you have in your circuit, you need to sample from at least 2 other circuits where you shift that particular parameter in each direction. Okay. What that means is that if you've got 10,000 parameters and you want to get the gradient of that circuit, you're going to have to sample from at least 20,000 circuits. So if you've got a massive circuit, you're going to spend all day just doing one gradient update. Effectively. If that wasn't bad enough, quantum circuits are also stochastic. Right, so it's not like a neural network where you plug something in and it's deterministic and you just get your answer. Quantum circuits, you have to sample from them and estimate values, right? That adds an additional burden. Meaning that if you want to estimate something to error epsilon, you have to sample more or less 1 of epsilon squared times. So you put these two things together and you just find your sampling all day long to optimize your circuits. So this is extremely different to what you get in backpropagation, where you basically get the gradients at the same cost as just running the forward model. I did like a little case study to try and make this point. Okay, so this is a quantum machine learning case study. So what we're going to do is we take a variational quantum model. It's going to have this structure, which people call data re-uploading structure. Basically, these W unitaries are parameterized. These S1s are your data loading, and you load in one, say, input at a time. So this would be one image, for example. And let's say we want to do 10 epochs of gradient descent. And we're going to use the parameter shift rule because it's the only thing that we know that works. And we want some precision, of course, on this gradient. So let's just say we want something like 10 to the minus 3 precision on each of the components of that gradient vector. And we don't have infinite time or money or patience. So we're going to train just continuously for 1 month max. Okay. So you can take these reasonable parameters and then you can start to ask what's possible to do. You can make the following plot. So on the y-axis, we have the maximum number of parameters in your quantum machine learning model. Okay. On the x, we're going to have the data set size. Okay, and then each of these lines corresponds to a quantum computer that is working at a different clock rate or sample rate. Okay, 1 kilohertz, it's maybe a bit pessimistic. Most people expect a megahertz computer to be more or less in the right ballpark. A gigahertz quantum computer is very few people, I think, expect to get that that fast, basically, with quantum computation.
What are you computing per, like in 1 hertz? You compute the cost function, or you measure the circuits?
That's how many times I can sample. So 1 kilohertz computer will generate me 1,000 bit streams every second. Okay, so what you're seeing on this graph is basically what this means is that if you take the kilohertz case, what is possible is everything which is below this line. Okay, and if you look at the max parameters, and this is 1. Okay, so here you can have 1. Everything below here, you've got less than 1 parameter. So it's only for very tiny data set sizes where you start to have like maybe 100 parameters if you're lucky. Okay. So that's clearly out of the question. Megahertz things, yeah, they get better, but you see basically limited to about 100 parameters, and even in the gigahertz, nowhere near the deep learning sort of size of models here. It's just 10,000. And then it gets. So there was a line here that's not very clear, but the other thing you see is that up here is the overparameterized regime where deep learning does well. Basically, you can't even get there with a gigahertz computer. And if you take a specific data set like the MNIST hand enrichment digits, which has 60,000 points, take some landmark neural networks from, from computer vision, right? You see that already beyond what we can do. So I would say this is looking pretty pessimistic in terms of scalability. So should we give up hope? Of course not. So what I think we really need to do is to focus on specific circuit structures that will allow us to go beyond the limitations of the parameter shift rule. And as I'm going to try and convince you in this talk, one way to do this is to use something called commuting quantum circuits. And that's what I'll talk about in the rest of the talk. And it's going to be split into two parts. The first part is going to be about how you can actually design specific circuit structures which do allow you to have the same sort of scaling and gradient behaviors you get in backpropagation. The second one is going to be to do with the generative learning, and potentially even more extreme. I'm going to show it's possible to train generative models, quantum generative models, without ever having to touch the quantum computer. Just do it on your laptop. There's many reasons why that's good as well. Okay, so this is the first part. It's based on this paper. It's published on the ArXiv at least, so check it out if you're interested. Okay, so I should explain to you the type of circuits that this works for. Okay, so it's going to be a method to go beyond parameter shift, have backpropagation like gradient estimation, and it's for this specific class of circuits. They look as follows. Okay, you have the usual, zero computational basis input. Then you can do whatever you like here. This is an arbitrary unitary, but it's not parameterized. Okay, it's just fixed. And then you're going to have something called a commuting circuit. Okay, and these consist of parameterized gates. Okay, so the usual e to the I generator parameter. But what's important is that the generators, these gates, so these matrices Gj, they all have to commute with each other. So they could all be a diagonal into X basis or Z basis or some basis. And then finally, we need to measure something, and the thing we're going to measure is going to be a Pauli word in some subsets of the qubits. Okay, so ZZZ, for example. That's the setup. There's going to be a few equations, but yeah, it's quite easy to see why this is the case. So I'll try to explain it for those of you that are familiar with this sort of thing. So what happens is when you take the expectation value, you end up with something that looks like, psi 0, u observable, u dag of psi 0. When you take the partial derivative of that, what happens is that your theta j comes down from the exponential along with the gj, but then that gj commutes with all the other generators, so it commutes with all the gates, and you can bring it to the middle of the expression. And long story short, when you do this, it's very easy to do. You see that the partial derivative basically looks like you're measuring this commutator on the state psi 0 u, where I'm sorry, I should have said psi 0 is this u followed by this arbitrary state. Okay, so that's what I just said, right? Effectively, getting these partial derivatives is like measuring these operators, which are commutators on this state. Another funny thing then happens, which is very easy to show, and I won't show it. These guys all commute with each other. That just follows from the fact that the GJs, they commute and the Pauli algebra, basically. And so because they all commute with each other, well, it means that they can be measured simultaneously. Okay, so that it means there is a basis in which you can measure all of these operators at the same time. And each of these operators gives you a partial derivative. So by measuring them all at the same time, you get all of the partial derivatives at the same time. And what that means is you have a constant scaling with respect to the number of parameters. You get everything. Okay, this is very different from parameter shift, where you'd have to go through every single parameter to do something. And it gets even crazier. Okay, so in practice, what would you do, right? You find the unitary which diagonalizes your operators. You would then do it after the circuit. You would sample, and then from that, you'd be able to work out all the gradient components. You can show, which was a surprise to us, that not only do you get the gradient, you get all partial derivatives of any order from these statistics, which is mad. It comes with the caveat that the higher up the order you go, the variance in your estimator increases exponentially. But still, you even get second order information from this. Which I think is something probably you don't even get in your lab, so I'm not sure. Okay, so if we return back to our plot, right, you can now ask what's possible. Basically, the scaling didn't depend on the number of parameters, so you can sort of forget about the y-axis now. The only question is, how big could the data set be? And you find, yeah, with a gigahertz, it's still pretty bad. A megahertz computer, you can handle data sets that are like 300,000 points large. In gigahertz, you could get really big. So, yeah, to some extent, this is really solved the scaling.
Joseph, I'm very confused.
Okay, good. Thank you for saying.
No, I have a question. Like when you measure like higher partial derivative orders, right? How do you do it in practice? You need to compute the commutator of the commutator of the commutator, etc., etc.
Yeah.
But then, like you say, you get all orders for free and blah blah blah. But then you need to. This I don't really understand. Like, so there is a game with the coefficients in which you have this weighted combination, and then you compute it, and you have a rule.
Yeah, you just find that they all commute with each other. So
yes,
you can take the first order ones, and you get something like this, right? And then you check it out, and that's what they all commute. Then you can say, well, you know what? I can just take another partial derivative here, and I'm going to get, like you say, like a commutator or a commutator. And then you can ask, well, do those objects commute with these? You find they also do. And then you keep going, and you see, well, actually, everything commutes with each other. So there is a basis that reveals all of the information, not just the first order, but also the second, third.
Okay.
Leaving out a lot of details, you have to post-process the data in a particular way and so forth.
But this post-processing is kind of trivial, no? Because you have the decomposition, like you have this operator written in that basis, and that's it.
Yeah, you just need to know the eigenvalues, but it's possible to figure them out. I lied a bit actually. You need two measurements here, and then you get everything. But yeah, for the sake of explanation, so it's just one.
Good. Okay. Sorry.
Well,
thank you.
Do you have any more questions?
No.
No.
Yes. Okay.
So we did one numerical experiment to try and figure out if this was useful or not. So caveat that it's just one, obviously. But we really did do it fairly. We didn't try and like advantage the circuit that we used. So what we looked at was just a 16-qubit problem with classifying what we call bars and dots data sets, or data set. So this is a bit like bars and stripes, but it's just one-dimensional where a bar looks like this, right? Zero here and one everywhere else. And dots is just sequential, like dotted pattern. We then add some Gaussian noise, and that gives us a labeled data set, and just try to classify it. We looked at a commuting circuit of the one I just showed you, but with the fact that we made it equivariant, so we chose the gates in a particular way to make sure the model was equivariant. That's a way you can do that. We did the same thing with a structure from the literature which doesn't have commuting generators, which is also equivariant. And we also looked at this something called a quantum convolutional neural network, which has also been floated around for this. So all of these are sort of designed to work with this translation invariant data. Okay. And yeah, surprisingly, we found that actually the commuting one, first of all, it required far fewer shots from the quantum circuit because the gradient estimation was much more efficient. These guys are using parameter shift. But it got like basically the best average classification as well. So take what you will from that, but it seems like they're not completely useless at least. So. Maybe one other thing I should say, which I've not mentioned, is we don't in general, we don't know how to simulate this. Okay, so there's no known classical dequantization yet, at least.
Because you can be whatever.
Yeah, actually, because we can put whatever, so it seems unlikely that will ever be the case. Okay, there's a few more things to say, but I'll just cover them fairly quickly. The first thing is you can generalize this structure to something we call a commuting block structure, where you have like blocks of commuting generators, and they have to like commute and generate between themselves. Sorry, commute or anti-commute. A bit of an involved definition, so I won't bother. But it was taken by these guys at Fujitsu, and they did a really cool paper where they proved a bunch of stuff about it, looked at symmetries. So if you end up reading more about this, I'd also check out that paper. Something which, I didn't realize until maybe after publishing, but I think maybe it's one of the most interesting things to think about as well. It actually, even though this model isn't universal, right? It's quite a restricted model because you have this commuting structure. You can do layer-wise training and get to universality, right? So one option that you have is to say, okay, I'm going to take a commuting block where everything is diagonal in the x basis. Okay, I train it in parallel. Then when I'm done, I fix it, and I'm going to train something now on the z basis, and you just repeat this process. You pay the price of having to do it layer-wise, but each of these layers has backpropagation and scaling, so you can have much more expressive models like this. So I think that's something interesting.
I understand that. Because in the optimal ways for like you train for the x basis and whatever will in general be fair. I'm super confused. Can you explain it again?
Let's say you want to do a classification task, right? So okay, maybe you have some input unitary here first as well. Okay, so one thing you could do is you could say, okay, well, I'm going to train my model to classify the data. I'm going to train it with generators that are all in the x basis that will commute, and I'll get some classification accuracy, I don't know, 0.8 or whatever, right? Then you can say, well, okay, but is there some way to make my model more expressive, okay, to do better? You can say, well, yeah, okay, now I can say just whatever parameters I found there, just fix them. Assume that's a fixed unitary, and then consider another commuting block of generators, now on a different basis. Because it's in a different basis, that allows you to increase expressivity. And maybe you start them with small values of the parameters, so you know your initial solution is sort of okay. But yeah, in principle, doing this, you can actually get to any. This is a universal ansatz. This structure, XZ. So you could do anything in principle with that.
Okay, it combines the identity, no? Your answers.
Combines what, sorry?
You can set the coefficients to 0, and then you have the identity, and then like for sure it's not worse.
Yeah, exactly. Okay. Yeah. Exactly. Maybe one more thing to say for people that are familiar with literature. There was a paper that came out shortly before ours, sort of saying the opposite. It was also highlighting this issue of the scaling compared to backpropagation. And in that, they proved that there isn't a general way to have backpropagation like scaling with parameterized quantum circuits. And what they did is they took an extremely general model. They put no structure into the model and said in the completely unstructured case, it's not possible. So our work doesn't contradict them. It just says, okay, you need to start building structure in order to get around things, which I think is a general issue that needs to be done. These no-go theorems. Okay. That's all I'm going to say about that part. So if there are any more questions, that would be the time.
Can I ask one question?
Sure.
Yes. So this first situation that same scaling is possible for commuting block circuits, don't you see this thing in your simulation that with 16 qubits? Like because, the next, this one. So here by non-commuting equivalent circuit, you mean that it is not even like commuting block circuits? No?
Yeah, the generators don't commute, but they're structured in a way to make it equivariant to translations.
Ah,
So you have X generators, Y generators, Z generators, all in the circuit. Whereas this one would just have, say, X.
okay. Okay, okay. Okay, thanks.
Okay, so yeah, let's move on to the second part. So this is really what's been occupying my mind for the last year or so. And as I said, it's to do with generative learning, and the main punchline is that yeah, we showed it's possible to train quantum generative models on just classical hardware. And this scales extremely well. Yeah, this first paper is published. I don't have the reference there, but it's on the archive, and this one's going to come out next week, hopefully. Okay, I guess many of you know what generative machine learning is, but I have a slide just to explain it. So, right, the setup is we have some ground truth distribution called P of X. Okay, and we sample from this distribution to get some data. This could be images. Here basically I'm representing bit strings because quantum computers sample bit strings, digital ones do. Right, and we also have something called a generative model. And a generative model is a conditional probability distribution, a Q that depends on some parameters phi. And we can also sample from this model to generate bit strings. And the general aim of generative learning, right, is to find some optimal parameters, theta, such that this conditional distribution in some vague way that I'm saying now approximates this ground truth, and this can depend a lot on the problem at hand. It's images that maybe just want them to be visually similar, for example. Okay, so that's generative learning. I'll now talk about the class of quantum circuits that we use to do generative machine learning. And we call them parameterized instantaneous quantum polynomial circuits. I say we call them, but these are quite well known. IQP circuits are quite well known in the literature. And they take a similar form to before, actually. So again, we're going to have commuting gates. Standard input, right? But now my commuting gates, the generators of the gates are going to be tensor products of Pauli X operators. So this one would be a single qubit rotation. This would be an XX rotation. And each of these is going to have its own separate trainable parameter as well. So there's a reason why these are quite well known in the literature, and the reason that they're well known is because they've been studied in complexity theory. And what the most recent result says in complexity theory basically is that if you want to sample the output distribution of circuits of this kind into inverse polynomial additive error, okay, then that would imply the collapse of the polynomial hierarchy to the second level, given you believe one of another two things which are apparently quite plausible, not complexity theorist. But long story short, people don't expect that we're going to find a classical algorithm to sample from this type of thing. Okay.
So you're not going to find what?
A classical algorithm that would be able to sample this. I mean, certainly, yeah, so if someone managed to do that for all possible structures and parameters, then it would imply this insane complexity thing, which is why they're being studied so much. But these circuits have a really weird sort of intermediate form of complexity. So whereas we expect that sampling from them is hard with classical devices, some things are easy. Okay, and what Martin van der Nest proved in 2009, this paper, a long time ago, and sort of forgotten since then, is he proved that if you want to do something else, so you don't want to sample now, okay, you just want to measure the expectation value of a Pauli word. Okay, so for example, this would be Z tensor Z. Estimate the expectation value. Don't sample from the distribution. That you can actually do That's easy to do, basically. There is an efficient classical algorithm to do that. I had a proof in my next slide. I don't know how much people want a proof. Probably not too much. I'll go, well, okay, maybe I'll get to the punchline. Thing is, it's not very difficult to prove this. Okay? You basically write out the expression, you throw in some Hadamard's identities here and there. So you develop things, you get this diagonal thing, but what you find is that the expectation value, okay, with respect to some subset of qubits A, and so this is a tensor product of Pauli Z's on some subset given by A. Basically, it just comes down to looking at the expectation value of this thing in square brackets, okay, where the expectation is taken with respect to bit strings Z sampled according to the uniform distribution of a cosine of basically a sum of your parameters of some linear algebra that relates to the gates of these bit strings, the observable. Okay, so it's just expectation, cosine, bunch of linear algebra. Of course, what you find is this cosine is bounded between +1 and -1, as it is, and this is what you have here is an expectation. Okay, so if you have an expectation of a bounded random variable, then the central limit theorem tells you you can estimate that expectation to inverse polynomial additive error by just taking a set of samples from this and calculating the empirical mean of that. Main point, this expression allows you to inverse polyadditive error estimates of expectation values. Yeah, so that, yeah, just to get away from the math a bit, that was just a proof of this statement. So.
But one question here, how many qubits can we measure? Like, are we restricted to just a subset of few qubits, or we can measure expectation values on all qubits?
All of those managed like, yeah.
Okay.
ZA can be any.
And it's more expensive if you do more, or?
No, you get the same error.
Okay. Thank you.
Okay, that's like the first ingredient that we need to understand. Okay, sampling hard, expectations easy. The second ingredient we need to understand comes from a paper from last year by Emmanuel Rudolph and a bunch of other people, and they showed something which I thought was quite surprising. You noticed it?
No. It's also somebody who was supposed to be a speaker. 2 weeks ago. And we forgot.
I can try and cover. So yeah, so what they look at in this paper is it's a loss function which is used to train generative models called the maximum mean discrepancy. It's not that common in the classical literature, but you do find it. It's had some success. The reason why people use it for quantum models is because it works when you have an implicit generative model, meaning that you don't have the ability to calculate probabilities, but you do have the ability to sample from the model, which is where you find yourself. That's what you find yourself in quantum machine learning, basically. And yeah, so this maximum mean discrepancy is sort of a statistical difference between two distributions. The cool thing that they show in this paper is that you can estimate it efficiently by just looking at Z-type expectation values. And so mathematically, they show that the MMD for this bandwidth, which sort of sets the length scale, between the generative model Q and some data set X, okay, that turns out also to be an expectation, where now you're sampling subsets of qubits. So A is a subset of qubits. According to this distribution, it's a simple distribution. I won't go into it, but you can sample from that of some function which depends on the expectation values, right, evaluated on your circuit and the data set. This function is simple, but to write it for clarity. But you're in exactly the same situation. You find that this F is also bounded, and the thing you want to calculate is an expectation with respect to a bounded random variable. So once again, you can get efficient inverse polyadditive error estimates of this, as long as you can get efficient polyadditive errors of these guys, the expectation values. Okay. So hopefully you see where I'm going with this. So they prove that the maximum mean discrepancy, you can get it by just sampling expectation values only, or estimating expectation values. We had this proof that if your circuit is an IQP circuit, then you can efficiently estimate these expectation values. So therefore, you can efficiently estimate, by combining two things, you can efficiently estimate the maximum mean discrepancy. Which means, actually, you have an efficient method to train these IQP circuits on classical hardware by going through the simulation algorithm. Which at first, maybe it's clear to you, but at first, I mean, some people are like, oh, no, that's not good, right? Because the training is classical, so now everything's classical. But, right, as we said, these circuits are hard to sample from. And in generative learning, what do you want to do? At the end of the day, you want to sample things, right? So even though the training can be done classically at inference time, which is what you're interested in, you will still need the quantum computer in order to deploy the circuit and sample from it. Okay, so you can have advantages at that time. And yeah, it goes without saying, but since most of the resources used to train quantum generative models are typically spent on doing the training, this is like an insane decrease in the resources that you need.
So MMD, in maximum mean discrepancy, works at the level of mean values, not at the distribution level. Like the question is like it's bounded by relative entropies or some stuff.
Sorry, I'm going to let you say again.
Like, I mean, if I train very well for the MMD,
Yeah.
then the distributions should be quite close.
Yeah.
According to the means, but if you look at like the whole distribution, it's also close or far away, or it's like
I guess
guarantee.
every metric has its own bias.
Yes.
I don't know if it's well understood exactly what the bias of the MMD is. What it sort of does, which was revealed by this theorem, is it does just do moment matching more or less.
Okay.
It looks at sort of low order-ish moments, and it just tries to match them basically. So that's one bias. But if it's zero, then it means that the distributions are the same and so forth. But yeah, I don't know how ideal it really is, and in practice how well it would work. People typically they want the log likelihood, right? It's not that. Okay, so we took that, and this was the first of the two papers related to this section, which I'll advertise quickly now. Is originally it wasn't going to be a paper, but we realized, okay, like we need to code up this thing, and then we're going to have to use it, so we just made a package, and we're like, okay, we have a package, so we might as well release it. So it's called IQP opt, and what this does is it does general sort of optimization of these parameterized IQP circuits. We do this in JAX. So basically, we code up this simulation algorithm and just use automatic differentiation to get ratings. I think it's really cool. I hope people start using it. It's very flexible, right? So this allows you to optimize any differentiable function of expectation values at the output of these circuits. It scales to hundreds of thousands of qubits and to millions of parameters on like a compute node, for example. And there's also this dedicated module that we developed to train generative models with the MMD. So this is what we used to do everything, but I think because we made it a bit more broad than just quantum machine learning, we hope other people pick this up and do something with it. Okay, so in the rest of the talk, I'll talk a bit about the numerics we did. Okay, so we coded this up. We looked at a bunch of generative learning tasks. We looked at 6 data sets. Okay, data sets are binary in nature because the quantum computer samples get strings. We go up to dimension 1000. Data sets are a mixture of synthetic and real world. I have a list of them on here. We trained 4 models. So one is this IQP model that I just explained, right? We also trained just a standard restrictive multiple machine in scikit-learn, not because we think it's the best model in the world, but it's an established model that serves as a sanity check basically. And we also coded up a sort of a generic energy-based model where the energy function was given by a feed-forward neural network. The reason originally for that was because we wanted to build graph structures into the circuit structure and into the energy function, which we didn't do too much in the end. That was the reason. Would be nice to do more, but limited time. And then finally something, I'm not going to speak a lot about, but one cool thing that you can do with this IQP model is you can come up with a classical model, which is equivalent to the quantum model where you decohere all the gates. So it's like every time you perform a gate, you just kill the coherence. And then you end up with a circuit which is in some sense like a classical analog of the quantum one, which basically corresponds to doing like stochastic bit flips on an input bit stream. So, but you can train that and you can see, okay, if the IQP model is doing better than the decohered version, then that gives you some evidence that coherence is actually being used in the model in some way. And yeah, we try to be as fair as possible. Of course, it's always hard to be completely fair, but we did a hyperparameter grid search for every model, every data set. It showed we tried to choose the hyperparameters and as reasonable as possible and so forth. We put a similar amount of effort into everything. So I'll just explain two maybe the most interesting things we saw. So, well, first of all, I guess the take home is that generative learning from high dimensional real world data is actually possible today with this method. This was data taken from D-Wave. Okay, so we found some paper where they quench a D-Wave system and they measure the spins, 484 of them. They get a distribution of the spins. So we sort of just stole that data set and we're like, we're going to do generative learning on it. Why not? So we have a 484 qubit model. We have all-to-all connected 2 qubit gates. So you end up with over 100,000 parameters in your quantum model. And sort of funny thing that we saw here was that the IQP model was literally the only one of the 4 to give us reasonable values. Okay. So what you're seeing here is this is the test loss. The MMD test loss, so lower is better, for a bunch of different bandwidths, or if you like, length scales. So this one here corresponds to looking on average just at 2-body correlations. This is more looking at 15 body or something. But each of these is a different sort of length scale. So yeah, the quantum model just did better than the length scales.
Sorry, what is this bandwidth?
Yeah, so I didn't explain that, but when you have the MMD, you have to set a sort of length scale that you're looking at.
Okay, for the expected values, like which.
It's basically there's a kernel in the definition of the MMD, and we use the radial basis function kernel, Gaussian, and you need the side on the standard deviation that defines that kernel.
Okay,
which
it's not like how many bodies correlations are you?
It translates to that, yeah.
Okay.
So when you write the MMD, it just looks like a sort of length scale basically of the distances that you're looking at. But when you write the MMD out in terms of expectation values, it translates to the bodiness of the corresponding expectation values, such that this is like 2-body and this is something like
that is decreasing. Like the last one is smaller than the.
Yeah, it's inversely. Yeah.
Okay.
A bigger bandwidth means smaller bodiness of the operators. Don't ask me why, but it does.
Okay, whatever.
Yeah. Cool. So this also supports a bit, something you hear, which I always complain about a bit. People saying that I know, quantum models are better on quantum data. I was like, are they really? Why? Apparently they are, at least in this experiment. So just for a bit more info, so this is looking at the covariance matrices of the data for each of the models, right? So this is what the covariance matrix looks like for the true data. So these are all just two-body correlations. And you see the IQP model, it's learned the general structure, but you see it, the correlations aren't as strong as they should be, right? But the structure's there. And what you see with the RBM is it basically mode collapsed. You see that some of these values are 0 on the diagonal, which means that the variance of the covariance was 0. So it just had massive problems of training. But that was after hyperparameter optimization. So, and the EBM just failed completely to train. I sampled it like non-stop all day on a compute cluster, like 5 million training steps. And I don't know, didn't manage. So I did everything I could to make that train. Something else we looked at is actually published results from literature. So what is interesting is now that we have a model that we can train on large data sets, we can even compare it to like real world stuff, right? So we found this paper where what they do is they create artificial human genomes using generative classical neural networks. The point is basically in the genome, you have these points where you have variation, they're called single nucleotide polymorphisms. They typically take one of two values. So you have the standard or the variant. So your particular sequence is a bit string. And then you can get this for a population of humans and you can learn the distribution over these variants of the genome. What is cool is that they train a couple of models in this paper. So they train an RBM and a GAN on this data, and then they publish, they sample from their trained models and they publish the samples on their GitHub. So then we can take them and we can sort of compare stuff. Yeah, and what we found was that our trained IQP model was sort of somewhere in between the two of theirs. Okay, the green is their RBM and the pink is their GAN. So yeah, basically according to this metric, which admittedly is a bit unfair because we trained on that metric as well, we didn't. We're sort of doing okay. And maybe, okay, here again, I've just showed you the covariance data. The general structure again has been learned by the model. Correlations are a bit weaker. But yeah, basically we're able to learn and get decent results on real world genetic. It was 300,000 parameters. Last thing, which I think is really interesting as well, and it's a question I always get, which is that, what about the Brown plateaus? We just ignored the whole Brown plateau thing, and then we said, okay, we're just going to initialize our parameters in a non-silly way. So we initialize them using the covariance matrix of the training data. So we get the trained data, we look at the covariance, and basically, if two elements are highly correlated, then the corresponding parameter will be initialized with a large value. Okay? There's a reason why you do that, because IQP circuits sort of enact a coherent bit flip, so it makes sense that if they're more correlated, you'd have that parameter be stronger. That makes like an enormous difference, right? At first, we were just initializing randomly. We tried initializing close to 0, it wasn't working. We tried this, and suddenly, bam, everything worked. The lost plots, things converged like super quickly, very easily. So yeah, that was an interesting observation. Okay. That's it for the generative learning. I'm going to finish fairly soon with a bit of an outlook. So,
sorry, stopping the slide. Just a bit of curiosity. I'm interested. So let's say if you're going to try to input with a proper structure for the quantum, you can avoid the bottom plateau basically. Yeah. You got it right. Which is the okay. So otherwise, which type you have promised?
We tried uniformly at random, and yeah,
maybe
the last
goes well, maybe not.
We tried close to 0. Can't remember. I mean, the last one is good. It's always hard to know. I mean, you try lots of different heuristics, and then when one works, maybe you just stop. But yeah, this worked. Yeah. Okay, so outlook. I think if we want genuinely useful models, we need two things. One is
Sorry, one question on Stephen. You mentioned before, I don't know if you,
Yeah.
it must be the decoherence results. Do you have any of that?
Yeah, so I didn't go into them too much, but you can see the name. So this, the IQP model is this blue one here.
Yeah.
The one where you decohere, it basically does the same as random data. So it really failed to train it with polyfill. There is a weird thing where the RBM and you can do worse than random data.
Yeah.
Seems very strange. It's because this are really serious mode claps, and that seems to hurt the MMD more than just like randomly doing stuff because you're so out of distribution. See, it's strange, but I don't think there's a mistake. And yeah, these models also weren't trained on the MMD. They were trained on the not likelihood of proving persistent divergence, persistent contrastive divergence. So yeah, the training messed up terribly, and the MMD ended up being worse than just random data.
But if you instead of testing with the MMD, you test like a callback layer or something different, like in SAS, or
I just can't because it's too it's intractable.
because you don't have it.
Yeah. There's like approximations and stuff, but it's very hard to do. And you see it from the covariance values. Something just went terribly wrong in training here. We didn't put more effort. I'm sure, like if you did put more effort, you would be able to get much better results. Maybe you would get even better results, but that was our point. Right? The hyperparameter, the grid sizes were actually bigger for the classical models, so we did more search. Really tried very hard. So I think this really just points out that it's surprisingly easy to train these things compared to energy-based models. All right. Yeah. So I think we need two things for useful models. The first is scalability, which I've spoken a lot about. The other is probably some sort of useful bias, and this I still don't have much to say with respect to the IQP structures. One thing that we can do is we can put like invariances which correspond to bit flip type symmetries into the distribution, like make the distribution invariant to flipping all the bits or something. I don't think that sounds super interesting, but yeah, I think we need a lot more work in understanding that as well. And then maybe last thing, like it's a bit opinionated maybe, but like what we did, a lot of people maybe would have said it was impossible if you just took some like no-go theorems at face value. You know, there's no backpropagation scaling. You know, you can't train because of band plateaus and so forth. Like we just went ahead and did it. Like so, I think people need to maybe not take no-go theorems too seriously. Remember that they apply to very general situations, and machine learning is not done in a very general situation. I mean, also remember what happened in classical machine learning, where for a long time it wasn't supposed to work, but deep learning was never supposed to work. It did. So I'm not convinced that the current sort of negative theories in QML really give a clear picture of what's ultimately possible. I think people are maybe too pessimistic, so I think I have to be a bit more optimistic and just try and do stuff. It's my opinion. Okay, thank you.